is a fact that should keep you up at night. Every single galaxy outside our little neighborhood, every spiral, every elliptical, every dim smudge of light across the entire observable universe is moving away from us. And not just drifting, accelerating, getting faster every second. Right now, as you hear these words, galaxies at the edge of what we can observe are receding at speeds that make the speed of light look quaint. And here is the part that should genuinely unsettle you. There is nothing anyone can do about it. Not in principle. Not with infinite technology. Not with the combined energy output of every star that has ever existed or will ever exist. The expansion of the universe is the one process in all of physics that cannot be stopped, reversed, slowed down, or even meaningfully resisted. And the reason why goes so much deeper than you think. Because the expansion of the universe is not a thing that is happening. It is not an event. It is not a force pushing galaxies apart. It is a property of existence itself. Asking how to stop the expansion of the universe is like asking how to stop time from passing or how to make 2 + 2 equal something other than 4. You are not fighting a process. You are fighting geometry. You are fighting the shape of reality. And reality, it turns out, does not negotiate. To understand why the universe expands and why nothing in the laws of physics permits it to stop, we need to go back to a time when nobody believed it was expanding at all. A time when the smartest person who ever lived was so convinced the universe was static and eternal that he deliberately broke his own equations to make them agree with him. And a time when a quiet astronomer in Arizona was making observations so strange, so completely inexplicable, that the scientific community essentially pretended they didn't exist. The year was 1912. The place was Lowell Observatory in Flagstaff, Arizona, a facility best known at the time for its founder, Percival Lowell's slightly embarrassing obsession with canals on Mars. Working there was a man named Vesto Slipher, and in September of that year, Slipher pointed a 24-inch Clark refractor telescope at the Andromeda Nebula and did something deceptively simple. He measured the light coming from it, split it into its component wavelengths using a spectrograph, and compared the resulting spectrum to what he expected. What he found made no sense. The spectral lines, those precise fingerprints that every chemical element leaves in light, were shifted, displaced toward the blue end of the spectrum by an amount that corresponded to a velocity of roughly 300 kilometers per second. Andromeda was rushing toward us faster than anything anyone had ever measured in the sky. Slipher reported his results on February 3rd, 1913, and the astronomical world was stunned, but not alarmed. One object moving quickly was interesting, not revolutionary, but Slipher kept observing. He turned his spectrograph on nebula after nebula, the fuzzy smudges that astronomers of the era couldn't yet confirm were galaxies beyond our own Milky Way. By April of 1913, he had measured the Sombrero Nebula receding at over 1,000 kilometers per second. By 1914, he had measured 15 of these spiral nebulae, and something deeply strange had become impossible to ignore. 12 of the 15 were moving away from us. Only 3 were approaching. By 1917, he had catalogued 25 objects, and the pattern was overwhelming. 21 were receding, with speeds reaching up to 1,800 kilometers per second. By 1922, his total reached 41 objects, almost all fleeing from Earth in every direction. At the 1914 meeting of the American Astronomical Society, held at Northwestern University, Slipher presented his findings to a packed room. The audience gave him something almost unheard of in scientific gatherings: a standing ovation. Sitting somewhere in that audience was a young graduate student named Edwin Hubble, who would later get all the credit for what Slipher's data was screaming. But Slipher couldn't finish the puzzle. He had velocity measurements, beautifully precise ones, but he had no distances. He knew how fast these objects were moving, but he had no idea how far away they were. And without distance, the relationship between speed and separation, the relationship that would reveal the expansion of the universe, remained invisible. His results were published in the Lowell Observatory Bulletin and the Proceedings of the American Philosophical Society, journals so obscure that they barely rippled beyond the small community of people who already knew Slipher's name. The man who first measured the expansion of the universe published his findings where almost nobody would read them. Meanwhile, on the theoretical side, something equally extraordinary was happening, and nobody was paying attention to that either. In 1922, a Russian mathematician named Alexander Friedmann sat down with Einstein's field equations, the mathematical heart of general relativity, and did something Einstein himself had refused to do. He solved them honestly. Einstein's equations describe the relationship between the curvature of spacetime and the distribution of matter and energy within it. They are elegant, powerful, and unforgiving. And when Friedmann applied them to a universe filled uniformly with matter, the equations gave him three possible answers. The universe could be expanding, it could be contracting, or it could be balanced on a knife's edge between the two. The one thing it could not do, the equations insisted, was sit still. A static, eternal, unchanging universe was not just unlikely, it was mathematically unstable. Like a ball balanced on the tip of a needle, the slightest perturbation would send it rolling in one direction or the other. Friedmann published his results in June of 1922 in Zeitschrift für Physik, one of the leading physics journals in the German-speaking world at the time. His paper was titled On the Curvature of Space, and it ran only a few pages. It was mathematically rigorous, it was correct, and Albert Einstein rejected it. Einstein published a note in the same journal claiming Friedmann had made a calculation error. He hadn't. Friedmann sent Einstein a detailed letter walking through every step of the derivation. Einstein checked the work again, realized the mistake was his own, and published a retraction in 1923, admitting that Friedmann's results were, in his words, both correct and clarifying. But Einstein still didn't believe the universe was actually expanding. The math allowed it. Einstein's gut said otherwise, and in 1922, Einstein's gut carried more weight than almost any equation. Friedmann never saw his ideas vindicated. He contracted typhoid fever and died on September 16, 1925, at the age of 37. One of his students was George Gamow, who would later develop the theory of Big Bang nucleosynthesis and predict the cosmic microwave background radiation Friedmann changed the course of cosmology and died before the course had time to change. But Friedmann wasn't alone. 5 years later, in 1927, a Belgian Catholic priest named Georges Lemaître independently arrived at the same conclusion. Lemaître was an unusual figure in physics. He had served as an artillery officer in World War I, earned his doctorate from the Catholic University of Leuven, studied with Arthur Eddington at Cambridge and Harlow Shapley at MIT, and was ordained as a priest in 1923. He moved between the worlds of physics and theology with a comfort that baffled many of his colleagues. Lemaître's paper appeared in the Annales de la Société Scientifique de Bruxelles under a title that said everything: a homogeneous universe of constant mass and increasing radius, accounting for the radial velocity of extragalactic nebulae. He didn't just predict expansion. He combined his theoretical framework with actual observational data, using Hubble's distance estimates and Slipher's velocity measurements, and calculated the expansion rate. He got a value of roughly 575 to 625 kilometers per second per megaparsec. The number was off by a factor of about 8 compared to modern measurements, but the methodology was sound and the conclusion was correct. Here is where the story gets painful. When Lemaître's paper was translated into English for the monthly notices of the Royal Astronomical Society in 1931, key paragraphs were removed. The paragraphs containing his calculation of the expansion rate. The paragraphs that would have established his priority over Hubble's 1929 result. For decades, historians assumed the translation was censored, perhaps by Eddington or by the journal editors. But in 2011, astrophysicist Mario Livio discovered the truth in the Royal Astronomical Society's archives. Lemaître himself had removed the paragraphs. He wrote that he did not find it advisable to reprint the provisional discussion of radial velocities, which is clearly of no actual interest. His modesty cost him credit for one of the greatest discoveries in the history of science. It wasn't until October of 2018 that the International Astronomical Union voted, 78% in favor, to rename Hubble's law as the Hubble-Lemaître law. The recognition came 52 years after Lemaître's death. Now, about Hubble. Edwin Hubble had access to something nobody else did. The 100-inch Hooker telescope at the Mount Wilson Observatory in California, which was the most powerful telescope on Earth at the time. Using this instrument, Hubble did something in 1924 that changed astronomy forever. He identified Cepheid variable stars in the Andromeda nebula, and by measuring how fast they pulsed, he could calculate how far away they were. This technique worked because of a discovery made by Henrietta Leavitt. In 1912, Leavitt had found that brighter Cepheids pulsed more slowly. If you measured the pulsation period, you knew the true brightness. If you compared the true brightness to the apparent brightness, you knew the distance. It was a cosmic measuring tape, and Hubble was the first person to extend it beyond the Milky Way. His measurements proved that Andromeda was far too distant to be inside our galaxy. The spiral nebulae were other galaxies entirely, vast island universes separated by millions of light years of empty space. The universe was suddenly incomprehensibly larger than anyone had imagined. And then Hubble did the thing that made him immortal. He took his distance measurements and combined them with Slipher's recession velocities. And this is where the history gets complicated, because Hubble's 1929 paper barely mentioned Slipher. The velocity data that made the entire discovery possible, the measurements that Slipher had spent over a decade painstakingly collecting, were referenced almost as an afterthought. Hubble treated them as established facts rather than as someone's life's work. Slipher received a standing ovation in 1914 and near obscurity by 1930. He spent the rest of his career at Lowell Observatory, eventually becoming its director, and died in 1969, having never received the recognition that his contribution warranted. Historians have been working to correct this injustice ever since, and the renaming to the Hubble-Lemaître law was at least a partial acknowledgement. But Slipher's name still isn't in it. The result, published in March of 1929 in the Proceedings of the National Academy of Sciences, was a simple graph with a profound implication. Distance on one axis, velocity on the other, and the points fell along a line. The farther away a galaxy was, the faster it was moving away from us. The relationship was linear, direct, and undeniable. This is Hubble's law. Now, the Hubble-Lemaître law. The recession velocity of a galaxy equals the Hubble constant times its distance. A galaxy twice as far recedes twice as fast. 3 times as far, 3 times as fast. And this wasn't because galaxies were fleeing from some cosmic explosion at a central point. It was because space itself was expanding everywhere at once. Imagine dots painted on the surface of a balloon. As you inflate the balloon, every dot moves away from every other dot. No dot is the center. Every dot sees every other dot receding. And the farther apart 2 dots are, the faster they separate. That is what the universe is doing. Not to objects in space, to space itself. Hubble's original estimate for the expansion rate was about 500 kilometers per second per megaparsec. This was wildly wrong, off by a factor of 7, because he confused 2 different populations of Cepheid variable stars that have different intrinsic brightnesses. Walter Baade caught the error in 1952. Alan Sandage refined the value further, and today, the best measurements put the Hubble constant somewhere around 67 to 73 kilometers per second per megaparsec. But here is the thing about that range. Somewhere between 67 and 73 is not how precise measurement is supposed to work. The fact that we have 2 numbers that refuse to agree is one of the biggest unsolved problems in all of cosmology. And we will come back to it later because it might mean that our entire understanding of the universe is incomplete. First, though, we need to talk about what Einstein did when he heard that the universe was expanding, because it is one of the most famous blunders in the history of physics. In 1917, 2 years after publishing General Relativity, Einstein applied his field equations to the universe as a whole for the very first time. The equations told him the universe couldn't be static. It had to be expanding or contracting. Einstein didn't like this. Nobody in 1917 liked this. The prevailing belief, shared by virtually every physicist and philosopher alive, was that the universe had always existed and would always exist, unchanging, eternal, infinite. So Einstein cheated. He added a term to his equations, a fudge factor he called the cosmological constant, represented by the Greek letter lambda. This term acted as a kind of anti-gravity, a repulsive force built into the fabric of space that would perfectly counterbalance gravitational attraction and keep the universe static. He presented the modified equations to the Prussian Academy of Sciences on February 8, 1917, and for 12 years the cosmological constant held. Then Hubble published his results in 1929, and Einstein's static universe collapsed. When confronted with the evidence, Einstein reportedly called the cosmological constant his greatest blunder. The exact quote comes from physicist George Gamow, who attributed it to a personal conversation in his 1956 Scientific American article, and later in his 1970 autobiography. No primary written source from Einstein exists, and some historians question whether he ever actually used those exact words. But the sentiment was genuine. Einstein felt he had missed the chance to predict the expansion of the universe, that his aesthetic preference for a static cosmos had blinded him to what his own equations were trying to tell him. He removed the cosmological constant. He assumed it was zero. He thought the matter was settled. He was wrong about that too. But we won't get to that part for another 70 years. Now here is where we need to stop and really carefully think about what expansion means. Because almost everyone gets this wrong, and getting it wrong makes it impossible to understand why expansion can't be stopped. When you hear that galaxies are moving away from us, the natural picture that forms in your mind is an explosion. A bomb goes off, and shrapnel flies outward in every direction. Galaxies are the shrapnel. Space is the room the shrapnel flies through. And if you could somehow apply a big enough force, you could slow the shrapnel down, stop it, maybe even pull it back together. That picture is completely, fundamentally, catastrophically wrong. Galaxies are not moving through space. Space itself is expanding. And there is a difference between those two statements that is so profound, it changes everything about how you should think about the universe. Here is a thought experiment that might help. Imagine baking a loaf of raisin bread. You mix raisins into the dough and put it in the oven. As the dough rises, every raisin moves away from every other raisin. A raisin that started 2 centimeters from yours is now 4 centimeters away. A raisin that started 4 centimeters away is now 8 centimeters away. The more distant raisin appears to be receding twice as fast, not because it is moving faster through the dough, but because there is more dough between you and it, and all the dough is expanding at the same rate. No raisin is the center of the expansion. Every raisin sees every other raisin moving away. The dough is the universe. The raisins are the galaxies. And the oven is, well, there is no oven. There is nothing outside the dough. The dough is all there is. But this analogy breaks in a crucial way. A loaf of bread has edges. The universe, as far as we can tell, does not. A loaf of bread expands into the surrounding air. The universe does not expand into anything. There is no outside. There is no space beyond space waiting to be filled. When physicists say the universe is expanding, they mean that the metric, the mathematical rule that defines distance between points, is changing. They mean that the definition of far away is getting farther. And not everything expands. This is important. Your body is not getting bigger. The Earth is not swelling. The Milky Way galaxy is not growing. The entire local group of galaxies, the roughly 80 galaxies gravitationally bound to one another within a few megaparsecs, is holding together just fine Expansion only dominates on scales larger than roughly 100 megaparsecs, about 300 to 26 million light-years. Below that scale, gravity and electromagnetic forces hold structures together. Atoms are bound by electromagnetic forces roughly 10 to the 40th times stronger than any expansion effect at atomic scales. As physicist Sabine Hossenfelder has pointed out, the solutions to Einstein's equations that describe galaxies simply don't expand. It is not that galaxies expand by an unnoticeably small amount. They don't expand at all. The equations that govern their behavior are different equations than the ones governing cosmic expansion. Now consider two galaxies, separated by 1 billion light-years, both sitting perfectly still in their local region of space. Neither one is firing rockets. Neither one is being pushed or pulled by any force. They are as motionless as anything can be. But tomorrow, the distance between them will be larger than it is today. Not because either galaxy moved, because the space between them grew. New space appeared in the gap, stretching the distance like someone pulling on both ends of a rubber sheet. The mathematics that describes this is called the Friedmann-Lemaître Robertson-Walker metric, named after 4 people who contributed to its development at different times and in different countries. And it is an exact solution to Einstein's field equations for a universe filled uniformly with matter and energy. The key quantity in this metric is something called the scale factor, usually written as A of dt, which describes how the distances between objects change over time. When the scale factor increases, distances grow. When it decreases, they shrink. At the moment of the Big Bang, the scale factor was essentially 0, meaning all distances were compressed to nothing. This distinction between motion through space and expansion of space has consequences that border on the absurd. For instance, there are galaxies right now, galaxies we can see with our telescopes that are receding from us faster than the speed of light. If you measure the rate at which the distance between us and a galaxy at the edge of the observable universe is increasing, you get a number that significantly exceeds 300,000 kilometers per second. According to a detailed analysis published by Tamara Davis and Charles Lineweaver in 2004, all galaxies above a redshift of roughly 1.5 to 3 are currently receding faster than light. This does not violate Einstein's special relativity. Special relativity says that nothing can travel through space faster than light. But the galaxies aren't traveling through space. Space is expanding between us and them. There is no speed limit on the expansion of space itself, because expansion is not motion. It is geometry changing. As physicist Sean Carroll has explained, there is no well-defined notion of the velocity of distant objects in general relativity. The rule against faster than light speeds only refers to relative velocities between two objects passing right by each other in the same local region of space. And this is exactly why you cannot stop the expansion. You cannot apply a force to counteract it, because it is not a force. You cannot build a wall to contain it, because there is no edge. You cannot push against it, because there is nothing to push against. Expansion is a property of the geometry of spacetime, described by the metric tensor in general relativity, and asking how to stop it is like asking how to stop a triangle from having 3 sides. It is baked into the mathematical structure of reality itself. But the story gets worse, much worse. Because for the first 70 years after Hubble's discovery, physicists assumed that even though the universe was expanding, it was at least slowing down. Gravity, after all, is attractive. Every galaxy pulls on every other galaxy. Over billions of years, this mutual gravitational attraction should be acting like a cosmic brake, gradually decelerating the expansion. The universe might expand forever, but it would do so more and more slowly, like a ball thrown upward that never quite stops rising. In 1998, two teams of astronomers set out to measure exactly how much the expansion was decelerating. They expected a straightforward result. They got the biggest shock in the history of cosmology. The first team was the Supernova Cosmology Project, led by Saul Perlmutter at the Lawrence Berkeley National Laboratory. It had been operating since 1988. The second was the High-Z Supernova Search Team, founded in late 1994, led by Brian Schmidt at the Australian National University, with a young postdoc named Adam Rees, doing the critical data analysis at the University of California, Berkeley. Both teams were using Type 1a supernovae as cosmic distance markers. A Type 1a supernova occurs when a white dwarf star, the dense remnant of a dead sun, steals matter from a companion star until it reaches a critical mass threshold of about 1.44 solar masses, known as the Chandrasekhar limit. At that precise mass, the white dwarf can no longer support itself against gravity, and it detonates in a thermonuclear explosion so bright it briefly outshines its entire host galaxy, roughly 5 billion times brighter than our Sun. Because these explosions happen at nearly the same mass every time, they produce nearly the same peak brightness, making them excellent standard candles. You measure how bright the supernova appears in your telescope. Compare it to how bright it should be, and the difference tells you how far away it is. Both teams found supernovae that were dimmer than expected, not brighter, which would have indicated deceleration, dimmer. The supernovae were farther away than they should have been if the expansion was slowing down. The only explanation was that the expansion had sped up since the light was emitted. The universe was not decelerating, it was accelerating. Adam Rees has described the moment of realization in interviews, and it is worth lingering on because it captures something important about how science actually works. He ran the analysis multiple times, convinced he had made an error. He checked for dust contamination, which could dim supernovae and mimic the effect of greater distance. He checked for evolutionary effects, the possibility that ancient supernovae were intrinsically different from nearby ones. He checked everything. The result refused to go away. Brian Schmidt has said that when he first saw the data, he was equal parts thrilled and terrified. Thrilled because the result, if true, was the discovery of a lifetime. Terrified because extraordinary claims require extraordinary evidence, and nobody wanted to announce that the universe was accelerating only to retract it 6 months later. Perlmutter's team found the same thing independently, which was the critical piece. One team could be wrong. Two teams finding the same result using different supernovae, different analysis pipelines, different telescopes, and different people was much harder to dismiss. The High-Z team published first. Adam Rees's paper, Observational Evidence from Supernovae for an Accelerating Universe and a Cosmological Constant, appeared in the Astronomical Journal in September of 1998. The the supernova cosmology projects, confirmation followed in the Astrophysical Journal in January of 1999. Science magazine named the accelerating expansion breakthrough of the year for 1998. In 2011, Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics. And just like that, the cosmological constant was back from the dead. Einstein's greatest blunder turned out to describe something real. The universe contains a mysterious energy that fills all of space, exerts a repulsive gravitational effect, and is driving the expansion to accelerate. Scientists named it dark energy, which is essentially a fancy way of saying, we have no idea what it is. Here is what we know. Dark energy constitutes approximately 68% of the total energy content of the universe. Dark matter makes up about 27%. Everything you have ever seen, every star, every planet, every human being, every atom of every element on the periodic table accounts for roughly 5%. We are a rounding error in a universe dominated by things we cannot see, cannot touch, and cannot explain. Dark energy has an energy density of about 7 times 10 to the negative 30th grams per cubic centimeter. That is absurdly low. A cubic meter of empty space contains so little dark energy that you would need a volume larger than Jupiter to collect enough to power a flashlight. But dark energy fills all of space, and there is a lot of space, and it adds up to 68% of everything. The simplest interpretation of dark energy identifies it with Einstein's cosmological constant, a fixed energy inherent to empty space-time itself. But this simple interpretation runs face first into what many physicists consider the single worst theoretical prediction in the history of science. Quantum field theory says that empty space is not truly empty. It seethes with virtual particles, fleeting fluctuations popping in and out of existence far too quickly to observe directly. These fluctuations carry energy. They are the reason for the Casimir effect, the measurable force between two metal plates placed close together in a vacuum. The virtual particles are real in every physically meaningful sense. And when you calculate how much energy all these virtual fluctuations should contribute to the vacuum, using the Planck energy as a natural cutoff, you get a number that is 10 to the 120th power times larger than the observed value of dark energy. That is a 1 followed by 120 zeros. Not 10 times too big, not 1,000,000 times too big, 10 to the 120th times too big. If the vacuum energy were really this large, the universe would have either collapsed into a singularity immediately after the Big Bang or expanded so violently that no atom could ever form. This is called the vacuum catastrophe, and nobody has solved it. It is not a minor discrepancy that might be fixed by a better calculation. It is a chasm of 120 orders of magnitude between prediction and observation, and it has resisted every attempt at explanation for over 50 years. Some physicists consider it the most embarrassing problem in all of theoretical physics. The fact that dark energy exists at all, at the specific tiny value it has, is one of the deepest mysteries in science. And here is the property that makes dark energy terrifying, the property that makes the expansion of the universe truly and permanently unstoppable. Dark energy does not dilute. Think about what happens to matter as the universe expands. Take a cubic megaparsec of space filled with galaxies As space expands, that cube gets bigger, but the amount of matter inside stays the same. The density of matter decreases with the cube of the scale factor. Double the size, 1/8 the density. Triple the size, 1/27th the density. Matter spreads out, radiation does even worse. Photons lose energy as their wavelengths stretch with the expansion, so radiation density decreases with the 4th power of the scale factor. Double the size, 1/16th the density. But dark energy? Dark energy density stays constant. As the universe expands, the amount of dark energy per cubic meter remains exactly the same. More space means more dark energy. The expansion doesn't dilute it. The expansion creates more room for it. And because dark energy's gravitational effect is repulsive, more dark energy means faster expansion, which means more space, which means more dark energy, which means faster expansion. It is a feedback loop with no off switch. This is why dark energy is sometimes described as having negative pressure, with an equation of state written as pressure equals negative 1 times energy density times the speed of light squared. In general relativity, both energy density and pressure contribute to gravitational effects. For ordinary matter, pressure is positive and small compared to energy density, so gravity is attractive. But dark energy's pressure is negative and enormous, equal in magnitude to its energy density. This negative pressure generates a gravitational repulsion that overwhelms the attractive gravity of matter and radiation. About 4 to 5 billion years ago, the density of matter in the universe had diluted enough that dark energy became the dominant component. Since that tipping point, the expansion has been accelerating. And because dark energy doesn't dilute, it will remain dominant forever. The acceleration will continue, compound, and intensify for all eternity. But wait, there is an objection you might be forming right now. What if we could somehow remove the dark energy, neutralize it, cancel it out? Would the expansion stop then? No, it wouldn't. Even in a universe with zero dark energy, the expansion would continue. Dark energy drives the acceleration, but the expansion itself predates dark energy by billions of years. The Big Bang set the universe expanding, and in a universe without dark energy, that expansion would simply decelerate under the influence of gravity. In an open universe, where the density of matter is below a critical threshold, the expansion would slow down, but never stop. In a flat universe, which is what ours appears to be, the expansion would approach zero velocity asymptotically, but never actually reach it. The only scenario in which expansion reverses and the universe collapses back on itself requires either a closed geometry, which observations have ruled out, or dark energy that changes sign and becomes attractive, which nothing in physics currently predicts. So even if you could eliminate the thing that is making the expansion accelerate, you cannot eliminate the expansion itself. It has momentum. Not mechanical momentum in the traditional sense, but a kind of cosmic inertia built into the initial conditions of the Big Bang. The universe started expanding, and in the absence of a force strong enough to reverse it, which would require more energy than exists in the universe, it will never stop. And here is where it gets even more hopeless. Even if you had infinite energy and infinite technology, you would face a problem that makes all other problems irrelevant. The expansion is happening everywhere simultaneously. There is no center, there is no edge, there is no button. You cannot station yourself had some special location and push back against the expansion because there is no special location. Every point in the universe is expanding away from every other point. To stop the expansion, you would need to simultaneously affect the geometry of space-time at every point in an infinite, or at least incomprehensibly vast, volume. And special relativity limits the speed at which any influence can propagate to the speed of light. Think about this concretely. Suppose you invented a machine that could somehow locally freeze the expansion of space within a sphere 1 light-year in radius. Congratulations! You have frozen a region so small that the expansion within it was already negligible. Gravity and electromagnetic forces already dominate at that scale. You have done nothing that nature wasn't already doing. To affect expansion where it actually matters, on scales of hundreds of megaparsecs and larger, you would need to deploy your machine across a volume containing billions of galaxies, and you would need all the machines to activate simultaneously. But you cannot coordinate them simultaneously because signals between them travel at the speed of light, and the machines are hundreds of millions of light years apart. By the time your activation signal reaches a machine at the edge of the network, the universe has expanded further, the distances have grown, and the problem is larger than when you started. You are trying to empty an ocean with a bucket, while a rainstorm dumps water faster than you can scoop. Large regions of the universe are already causally disconnected from us. Light emitted from those regions today will never reach Earth. We cannot send signals to them, influence them, or even learn what they contain. The observable universe, the sphere from which light has had time to reach us since the Big Bang, has a radius of about 46.5 billion light years. But the actual universe, if it even has a boundary, extends far beyond that, perhaps infinitely. You cannot stop the expansion of a volume you cannot even access, much less comprehend. There is a concept in cosmology called the cosmic event horizon that makes this even more disturbing. The event horizon is the distance beyond which events happening right now can never affect us. Not in a billion years, not in a trillion years. Never. Because the expansion of space between here and there is so rapid that light from those events will never bridge the gap. That distance is currently about 16 to 18 billion light years. And here is the heartbreaking part. We can see galaxies that are already beyond our event horizon. They emitted their light when they were much closer, and that ancient light has had time to reach us. But we will never see those galaxies as they are today. We will never learn what happened to them. They are visible ghosts, light echoes of structures we have already lost contact with. Roughly 96% of the galaxies we can currently observe are already forever unreachable. They exist in our sky, but not in our future. Now, remember that disagreement about the Hubble constant I mentioned earlier? Somewhere between 67 and 73 kilometers per second per megaparsec? That number might sound like a minor discrepancy, a rounding error in the grand scheme of cosmic measurement. It is not. It is potentially the most important number in all of physics right now, and it is called the Hubble tension. Here's the problem. Two completely independent, extremely precise methods of measuring the expansion rate give answers that disagree by about 9%, and neither one appears to be wrong. The first method measures the cosmic microwave background, the faint afterglow of the Big Bang that fills the entire sky. The European Space Agency's Planck satellite mapped this radiation with extraordinary precision and used the patterns encoded in it to calculate the expansion rate. The answer was 67.4 kilometers per second per megaparsec, give or take about 0.5%. The second method uses the cosmic distance ladder, a chain of increasingly distant measurements built from geometric parallax at the base, through Cepheid variable stars in the middle, to Type 1a supernovae at the top. Adam Rees and the SH0ES team, standing for supernova H0 for the equation of state, have refined this method to extraordinary precision. Their answer is about 73 kilometers per second per megaparsec, give or take about 1%. The discrepancy exceeds 5 sigma in statistical significance, meaning there is less than a 1 in a million chance it's due to random error. Either one of the measurements has a systematic error nobody has found, or our understanding of the universe is missing something fundamental. And both of those possibilities are extraordinary. If there is a systematic error, it has eluded two of the most thoroughly scrutinized measurement programs in the history of astronomy. The Planck satellite's CMB analysis has been checked by multiple independent teams. The SH0ES distance ladder has been calibrated, cross-checked, and verified with multiple independent anchors. Hundreds of papers have proposed potential systematic errors. None have stuck. The measurements appear to be genuinely correct, which means the disagreement points to something wrong with our model of the universe. Possible explanations are proliferating. Early dark energy, which posits that a brief burst of dark energy in the first few 100,000 years after the Big Bang would have changed the expansion rate in a way that the Planck analysis doesn't account for. Self-interacting dark matter, which would alter the growth of cosmic structure. Modified gravity, which changes the relationship between matter and space-time on cosmological scales. Extra-relativistic species, meaning additional particles beyond the known ones that were present in the early universe and contributed to its expansion rate. Each of these proposals has consequences that extend far beyond the Hubble constant, potentially requiring revisions to the standard model of cosmology that has held firm for over 2 decades. The Hubble tension might be the crack in the foundation that reveals an entirely new understanding of the universe. Or it might be a measurement error that someone eventually finds. Nobody knows yet, but the fact that it persists stubbornly and at high significance suggests the universe is trying to tell us something. For years, many physicists hoped the James Webb Space Telescope would resolve the tension. JWST's infrared vision can see Cepheid variable stars more clearly than the Hubble Space Telescope, cutting through dust and resolving individual stars in crowded fields. In February of 2024, Rees and the SH0ES team published JWST observations of over 1,000 Cepheids in 5 galaxies that also hosted Type 1a supernovae. The results confirmed the local measurement with devastating precision, ruling out Cepheid crowding as an explanation at 8.2 sigma confidence. A larger JWST study, published in December 2024, found that Webb and Hubble agreed to within 2% on the Hubble constant. The measurement is correct. The tension is real. Meanwhile, Wendy Friedmann at the University of Chicago has been pushing alternative approaches using JWST. Her team uses different stellar indicators, specifically the tip of the red giant branch and J-region asymptotic giant branch stars, and has reported intermediate values around 69 to 70 kilometers per second per megaparsec. If confirmed, these results might thread the needle between the two competing measurements. But for now, the tension persists, and nobody can explain it. And then, in 2024, things got even more interesting. The Dark Energy Spectroscopic Instrument, known as DESI, sits atop a telescope at Kitt Peak National Observatory in Arizona. It uses 5,000 robotic optical fibers to simultaneously measure the spectra of thousands of galaxies and quasars, mapping their three-dimensional positions across enormous volumes of space. DESI is looking for baryon acoustic oscillations, frozen sound waves from the early universe that created a characteristic pattern in how galaxies are distributed. These patterns act as a standard ruler, a known distance scale that lets astronomers measure how the expansion rate has changed over time. DESI's first-year results, released in April of 2024, after analyzing over 6 million galaxies and quasars, found something unexpected. When combined with cosmic microwave background and supernova data, the results showed a preference for dark energy that changes over time. Not a cosmological constant, not a fixed, eternal property of space-time. Something dynamic, something that was stronger in the past and appears to be weakening. The statistical significance was 2.5 to 3.9 sigma. Intriguing, but not definitive. Then came the 3-year results, released in March of 2025. With over 14 million galaxies and quasars, the largest three-dimensional map of the universe ever constructed, DESI strengthened the finding dramatically. The preference for evolving dark energy reached 4.2 sigma, meaning 99.995% confidence, still technically below the 5 sigma threshold that physicists consider a firm discovery, but close enough to make every cosmologist in the world pay very careful attention. If DESI is right, if dark energy really is changing over time, then Einstein's cosmological constant is wrong. Not wrong in the sense that dark energy doesn't exist. Wrong in the sense that dark energy is not the simple, elegant, unchanging property of space-time that everyone assumed. It is something more complicated, something dynamic, perhaps a new quantum field that permeates all of space, a field that theorists have named quintessence, after the fifth element of ancient philosophy. And here is the twist that should genuinely blow your mind. Even if dark energy is weakening, the expansion still can't be stopped. A weakening dark energy would slow the acceleration, meaning the expansion rate would increase less rapidly. But it would not reverse the expansion. To reverse expansion, dark energy would have to change sign entirely, flipping from repulsive to attractive. Nothing in the DESI data suggests this. Nothing in any theoretical model that fits the data predicts it. The expansion may accelerate more slowly than we thought, but it will still accelerate. And even if the acceleration stopped completely, the expansion itself would continue from Big Bang momentum. The universe has stacked the deck. Multiple independent, reinforcing barriers make stopping expansion not just practically impossible, but conceptually incoherent. Expansion is geometry, not force. Dark energy doesn't dilute. The universe has no center or edge to manipulate. Gravity cannot compete on the larger scales. Information cannot travel fast enough to coordinate any intervention across the relevant distances, and even the initial momentum of the Big Bang guarantees perpetual expansion regardless of what dark energy does. There is also a theoretical result that makes this permanence feel almost inevitable. It is called the cosmological no-hair theorem. In physics, a no-hair theorem describes a situation where the final state of a system erases all memory of its initial conditions. The classic example is black holes, which are completely described by just 3 numbers: mass, charge, and spin, regardless of what fell in to form them. A black hole made of stars looks identical to one made of planets or old encyclopedias. The cosmological version says something similar about the universe. Any universe with a positive cosmological constant, meaning any universe with a dark energy like ours, will inevitably approach something called de Sitter space. De Sitter space is an empty, exponentially expanding spacetime that represents maximum entropy. It doesn't matter what the universe looked like at the start. It doesn't matter how matter was distributed, what structures formed, how galaxies clustered. Given enough time, everything dilutes, everything smooths out, everything converges to the same featureless, exponentially expanding void. De Sitter space is the cosmic endgame. It is the thermodynamic attractor, and once the universe reaches it, it stays there forever. This brings us to the question that every documentary about cosmic expansion eventually reaches. If the expansion cannot be stopped, what happens? Where is the universe going? And is the ending as bleak as the physics suggests? The short answer is yes. The ending is bleak. The long answer requires a timeline so vast, it makes the current age of the universe look like the opening frame of a film that runs for eternity. The most likely fate of the universe, given current observations, is something called the Big Freeze, sometimes called heat death. It is not dramatic. It is not sudden. It is the slow, inexorable dissipation of every structure, every source of energy, and every possibility of complexity in the entire cosmos. But before the freeze, there is one last, beautiful event. In about 4 to 5 billion years, the Andromeda galaxy will collide with the Milky Way. Right now, Andromeda is about 2.5 million light-years away, and it is heading toward us at approximately 110 kilometers per second. This happens despite the expansion of the universe, because our local group of galaxies is gravitationally bound. The mutual attraction between Andromeda and the Milky Way decoupled from the cosmic expansion over 10 billion years ago. On the largest scales, expansion wins. On local scales, gravity wins. And Andromeda and the Milky Way are very much local. The collision itself will be spectacularly slow. The first gravitational interactions will distort both galaxies into long tidal streamers, pulling ribbons of stars hundreds of thousands of light-years long. The cores will pass through each other, swing back, pass through again, and gradually merge over the course of about 2 billion years. The resulting galaxy has already been given a name: Milkomeda, sometimes called Milkdromeda, a name that sounds less like astrophysics and more like a bad milkshake. Individual stars are so widely spaced that actual stellar collisions will be exceedingly rare. If the Sun still existed, and it won't, because it will have ballooned into a red giant and swallowed the inner planets roughly 1 billion years earlier. The night sky would be transformed. Where we currently see Andromeda as a faint smudge, future observers would witness a swirling chaos of hundreds of billions of stars spreading across the entire sky, brighter and more dramatic than any event in the previous 10 billion years of cosmic history. Our solar system has a roughly 12% chance of being ejected from Andromeda entirely, flung into the void between galaxies, orbiting nothing, going nowhere, a dead star system drifting through empty space. After that merger, the clock really starts running. In roughly 100 billion years, every galaxy beyond the local group will have receded past the cosmic event horizon. The expansion will have carried them so far away so fast that their light will be permanently redshifted beyond detection. An astronomer living in Andromeda at that time would look up and see nothing, no galaxies, no cosmic microwave background, because the CMB will have been stretched to wavelengths larger than galaxies, making it completely undetectable. No evidence of the Big Bang, no evidence that the universe was ever anything other than a single galaxy floating in an infinite static void. Lawrence Krauss and Robert Scherer pointed this out in a 2007 paper that should be required reading for anyone who cares about the nature of knowledge. They showed that a civilization arising in the far future would have no way to discover cosmology's true history. The evidence will have been erased by expansion itself. Those future scientists would likely conclude that the universe had always been static and unchanging, a single galaxy in an infinite empty space, which is exactly what scientists believed before the 1920s. The universe will have circled back to the same wrong answer, but this time there will be no Slipher to measure redshifts, no Hubble to find the distance-velocity relationship, no Penzias and Wilson to accidentally discover the cosmic microwave background while troubleshooting pigeon droppings on their antenna. The physical evidence that would have allowed them to discover the truth will have been carried away by the very expansion they cannot detect. Think about what that means for a moment. It means that cosmological knowledge about the origin and fate of the universe itself, is time-dependent. There are truths about reality that can only be discovered during certain epochs. We happen to live during one of those epochs. In fact, we live during arguably the only one. The window opened when galaxies were close enough to study, but distant enough to show redshifts, and it will close when they recede beyond the event horizon. The universe handed us the evidence, and it is slowly taking it back. We live in a cosmically privileged era, possibly the only era in the entire lifespan of the universe when its true nature is observable. The window is open now. It will close, and it will never reopen. After 100 trillion years, roughly 10 to the 14th, the stelliferous era ends. This is the age of stars, and it is almost inconceivably brief on cosmic timescales. The smallest, most fuel-efficient red dwarf stars, the ones that burn hydrogen so slowly they glow barely brighter than a candle, will finally exhaust their fuel and go dark. Star formation will cease as remaining gas is consumed or expelled. Occasionally, two brown dwarfs, failed stars that never ignited hydrogen fusion, will collide and briefly produce a new star. But these events will be so rare that perhaps 2 or 3 new stars will form across the entire galaxy over trillions of years. The age of light is over. What follows is the degenerate era. The universe becomes a cemetery of stellar corpses, White dwarfs cool toward absolute zero over timescales that make trillions of years seem brief. Neutron stars spin down and cool. Planets drift through the darkness, frozen, orbiting dead stars that emit nothing. And then the corpses themselves begin to disappear. If proton decay occurs, and most grand unified theories predict that it does, though it has never been observed, then all ordinary matter is temporary. The current experimental lower bound on the proton's half-life is roughly 10 to the 34th years. Over timescales of 10 to the 34th to 10 to the 40th years, protons and neutrons would spontaneously disintegrate, converting white dwarfs, neutron stars, and planets into diffuse clouds of radiation and fundamental particles. Nothing solid would remain. Black holes, the most enduring structures in the universe, would be the last object standing. But Stephen Hawking showed in 1974 that black holes are not truly eternal. They emit Hawking radiation, a quantum effect where particle-antiparticle pairs form near the event horizon, and one particle escapes while the other falls in, slowly draining the black hole's mass. A stellar mass black hole, about 10 times the mass of our Sun, would evaporate in roughly 10 to the 67th years. The supermassive black holes at the centers of galaxies, with masses of millions or billions of suns, would last longer, but not forever. The most massive black holes would finally evaporate after roughly 10 to the 100th years. That number, 10 to the 100, is called a googol. Google, the company, was named after it, with a deliberate misspelling. After the last black hole evaporates, the universe enters the dark era. The only things remaining would be photons, neutrinos, electrons, positrons, and whatever dark matter is made of, all scattered through an infinite volume of space at temperatures asymptotically approaching absolute zero. No structures, no energy gradients, no possibility of work or change or complexity or life. Maximum entropy, thermodynamic equilibrium. The universe will be perfectly smooth, perfectly cold, perfectly dead, and perfectly eternal. If you could somehow stand in this universe and look around, you would see nothing. The photons will have been redshifted to wavelengths billions of light years long, oscillating so slowly that they carry effectively zero energy. The electrons and positrons will be so far apart that the average distance between any two particles could be measured in light years. Nothing will ever touch anything again. Nothing will ever interact with anything again. Every quantum of energy that once powered stars and warmed planets will have been distributed so evenly across so vast a volume that it is indistinguishable from absolute nothingness. The universe will be dead in the most complete sense of the word, not dead like a corpse, which still has structure and chemistry. Dead like the concept of death itself, applied to everything, everywhere, forever. In 1979, Freeman Dyson published a beautiful paper titled Time Without End in Reviews of Modern Physics. Dyson asked whether intelligent life could survive forever in an expanding universe by progressively reducing its energy consumption, thinking more slowly, and hibernating for ever longer intervals. His conclusion was cautiously optimistic. In a universe without a cosmological constant, where temperatures approach absolute zero but never quite reach it, an intelligent being could, in principle, make an infinite number of thoughts, using a finite total amount of energy. But dark energy ruins Dyson's calculation. The cosmological constant creates a minimum temperature in the universe, the Gibbons-Hawking temperature associated with the cosmic event horizon. This temperature is extraordinarily low, roughly 10 to the negative 30th Kelvin, but it is not zero. It represents a thermal floor below which the universe can never cool. And a thermal floor means a limit on the efficiency of computation, which means a finite total number of possible thoughts, which means that even the most clever civilization cannot survive forever. Dark energy doesn't just make the universe expand, it makes eternal life impossible. There is one final theoretical possibility worth mentioning, though it remains speculative and not currently favored by observations. If dark energy turns out to be phantom energy, meaning its equation of state parameter is less than -1, then its density would not just remain constant. It would actually increase as the universe expands. Phantom energy would grow stronger and stronger, eventually overwhelming every other force in nature. The timeline of a Big Rip is horrifyingly precise. In a hypothetical scenario where the equation of state parameter is -1.5, the Big Rip would occur in about 22 billion years from now. But the last few billion years would be where the real destruction happens. About 1 billion years before the end, galaxy clusters would be torn apart. The gravitational bonds between galaxies ripped like threads. About 60 million years before, individual galaxies would disintegrate, their stars scattered like sparks from a fire. About 3 months before, solar systems would become unbound, planets drifting away from their stars. In the final minutes, stars themselves would be ripped apart, their internal pressure overwhelmed by the expansion of space within them. In the final fraction of a second, roughly 10 to the -19 seconds before the end, atoms themselves would be torn apart, electrons stripped from nuclei, protons and neutrons disintegrating. And then space-time itself would cease to have a meaningful structure. The metric would diverge to infinity. The fabric of reality would simply stop being fabric. It is an ending out of a nightmare. But it is probably not our ending. Current measurements place the equation of state parameter very close to -1, and the DESI 2025 results actually suggest dark energy is weakening, not strengthening. So the Big Rip is unlikely, but it remains within the range of theoretical possibility, a reminder that the universe's expansion contains potential endings far more violent than the quiet heat death we currently expect. The European Space Agency's Euclid Space Telescope, launched on July 1st, 2023, is now orbiting the Sun-Earth L2 point alongside JWST. Over its 6-year mission, Euclid will survey 1/3 of the sky, mapping the distribution of galaxies and dark matter across 10 billion years of cosmic history. Its first major data release is expected in June of 2026, and it may confirm or refute DESI's hints of evolving dark energy. If Euclid agrees that dark energy is changing, the implications would be enormous. It would mean the cosmological constant is wrong, that the simplest explanation for the universe's acceleration needs to be replaced with something more complex, and that the future of the cosmos might be different from what we currently predict. But it would not mean the expansion can be stopped. Even evolving dark energy is still dark energy. Even weakening repulsion is still repulsion. And even without any dark energy at all, the expansion continues. There is something profound and unsettling about living in a universe whose most fundamental property is the creation of distance. Every second, the space between unbound structures grows. Every second, galaxies we can currently see slip a little further toward the cosmic event horizon. Every second, the observable universe gets a tiny bit larger, while the reachable universe gets a tiny bit smaller. We are surrounded by an expanding sphere of knowledge and a contracting sphere of possibility. And the gap between what we can see and what we can touch grows wider with every passing moment. And nobody asked for this. Nobody chose it. Nobody can change it. The expansion of the universe is not the result of a decision or an accident or a failure. It is the shape of space-time. It is written into the equations of general relativity the same way the Pythagorean theorem is written into flat geometry. Given the initial conditions of the Big Bang and the presence of dark energy, expansion is not just what happens. It is the only thing that can happen. Friedmann showed this in 1922 and died before anyone believed him. Lemaître showed it in 1927 and censored his own priority out of modesty. Hubble confirmed it in 1929 with observations that should have been Slipher's triumph. Einstein predicted it, denied it, fudged his equations to avoid it, and then spent the rest of his life regretting the fudge. Perlmutter, Schmidt, and Rees discovered in 1998 that it was even worse than everyone thought, that the expansion was accelerating, that the fudge Einstein introduced and then removed was somehow right all along. A century of brilliant people fighting the same conclusion, and the conclusion never budged. The universe is expanding, it is accelerating, and there is nothing that can be done. There is a version of this story that is depressing, the version where the heat death of the universe means everything is pointless, every civilization is temporary, every achievement is destined to be erased by an eternity of cold, empty nothing. But there is another version. The version where the fact that we figured this out at all is the remarkable thing. A species on a small rocky planet orbiting a medium-sized star in an ordinary spiral galaxy, one of at least 2 trillion galaxies in the observable universe, looked up, measured the light from distant objects, argued about the math for a century, discovered they were wrong about almost everything they believed about the cosmos, and correctly deduced the ultimate fate of reality, not approximately, not metaphorically, correctly, with equations that match observations to 5 decimal places. We exist in the one narrow window of cosmic time when the evidence is still visible. A few 100 billion years from now, the clues will be gone. The cosmic microwave background will be undetectable. The distant galaxies will have vanished. The universe will look eternal and static to anyone who comes after us. But we caught it. We saw the redshifts. We measured the acceleration. We found the microwave echo of the Big Bang. We mapped the distribution of galaxies across billions of light years and used frozen sound waves to measure the age and fate of everything that exists. We did this with telescopes and mathematics and stubbornness and a willingness to accept answers that made us uncomfortable. The universe is expanding, and it will never stop. But for one brief, improbable moment, something in the universe understood that, and that might be enough. If you want to go deeper into the physics that shapes our cosmos, check out the video on screen. And if you made it this far, subscribe. There is always more to unravel.